Okay, so I'll talk about supernova. So I may be in the wrong session, I don't know. This is based on a paper with my graduate student, Taigun, who left physics off as soon as this paper is published. But anyway, so I'll talk about spin flavor precession phase effects in supernova. And in order to talk about the spin flavor precession, I shall talk about neutrino magnetic moment for a bit. So even in the minimally extended standard model, neutrinos have a magnetic moment due to these loop diagrams. And the magnetic moment is supposed to be, probably close to 10 to the minus 20 Bohr magneton, because it also depends on the mass, and assuming that the neutrino mass is of the order of 0.1 electron volt. The magnetic moment of the neutrino expected from the standard model is extremely small, 10 to the minus 20 Bohr magneton. However, it's also possible that it is enhanced in beyond the standard model physics. So it's also useful to look at the experimental limits. Maybe I should use this one. The experimental limits usually come from the enhancement of electron neutrino scattering due to magnetic moment. So for example, the best experimental upper limit comes from the gamma collaboration, which constrains the electron antineutrino magnetic moment from the scattering of reactor neutrinos on electrons, and the upper bound is 10 to the minus 11 Bohr magneton. A similar upper bound actually comes from the analysis of dark matter experiments, because solar neutrino scattering on electrons is a background for dark matter searches. So a recent analysis of dark matter experiments puts a similar upper bound on electron neutrino magnetic moment. Also, slightly better upper bounds come from astrophysics, from an analysis by Georg. And this is due to the fact that neutrino magnetic moment enhances plasmon decay into neutrino antineutrino pairs. And if this happens very fast, then the red giants will cool too fast. So we have an upper bound of about 10 to the minus 12 Bohr magneton from this. But as you see, there is quite a large gap between the theoretical value and the experimental or observational upper bounds. Of course, I'm more interested in the effects of the neutrino magnetic moment on neutrino flavor transformation, and that depends whether neutrinos are Dirac or Majorana. So magnetic moment basically flips the neutrino spin, which flips the helicity. And if neutrinos are Dirac, then the wrong helicity states are just sterile. But if they're Majorana, then it's different. And I'm going to assume that neutrinos are Majorana. And I'm also going to assume that there are only just two flavors, which is enough for my purposes here. And I'll also follow the convention of calling the positive helicity neutrinos as antineutrinos. So the negative helicity neutrinos, I'll just call neutrinos, negative helicity degree of freedom. And the positive helicity degree of freedom, I'll call antineutrinos, because positive helicity Majorana neutrinos behave very similar to Dirac antineutrinos. So basically, in this case, the term, the multiplication of magnetic moment and magnetic field, in that sense, mixes neutrino and antineutrino degrees of freedom. And the corresponding part of the neutrino oscillation Hamiltonian would look like this, because the flavored diagonal components, actually in any basis, the diagonal components of the magnetic moment would vanish due to the reality condition on Majorana neutrinos. And part of the Hamiltonian relevant neutrino magnetic moment would look like this. Here, B is not the full magnetic field, it's just the component of the magnetic field, which is perpendicular to the directional motion of the neutrino. And since I have neutrino and antineutrino degrees of freedom mixing, I have I have to use a larger density matrix here. Here you see a 4x4 density matrix, and the 2x2 block diagonal components will correspond to usual neutrino-neutrino and anti-neutrino mixings, and the 2x2 off-diagonal blocks will correspond to neutrino-anti-neutrino mixing. And similarly, I have the Hamiltonian. All the mixing terms, vacuum mixing terms, and the method terms will be in the 2x2 block diagonals. And here I have the off-diagonal term. And of course, when I have something like this, in addition to the usual MSW resonance, which happens either in the neutrino sector or anti-neutrino sector, there is also neutrino anti-neutrino resonances. And these are called spin-flavor precession resonances. This is called spin-flavor precession because the magnetic moment flips both the spin and the flavor of the neutrinos at the same time. So that, of course, depends on the matter density. So here you see the condition for the MSW resonance. That's the usual MSW resonance condition. Here, N is the density in grams per centimeter cube. If I divide it by baryon number and multiply with the electron fraction, by E is the electron fraction. Here, I get the usual electron density. Spin-flavor resonance condition is very similar, except that I have a different factor, 1 minus 2 times the electron fraction here. So in this work, we kept the electron fraction constant, which is, of course, an approximation. And for this value of the electron fraction, the spin-flavor resonance always happens before the MSW resonance. So it happens at a higher density, as you can see here. And let me also talk a little bit about the density profile that we use here. So here we used a very simple pre-supernova model from this reference, which is indicated by this solid black line here. It's a pre-supernova model at t equal to 0 at the bounce time. And we superimpose on it a parametric shock wave. A parametric shock wave means we just modify the matter distribution with some parameters to imitate a shock wave. I mean, it's not from a real supernova model. These give us the red line, which is for 1 second, blue line for 2 seconds, and also for the other seconds. The dotted lines here are not very important. You can ignore them for the time being, but these are actually the best exponential fits to density, which we used for some very quick calculations, so you can basically ignore them. And the magnetic field profile that we use is somewhat on the stronger side. It's of the order of 10 to the 15 Gauss near the center of the supernova, and after that, it decreases with distance. So with that, we have this diagram for the spin-flavor precession and the MSW precession. It looks like this in a diagram. So we assume that the hierarchy is normal, which means that MSW resonance occurs in the neutrino sector between nu E and nu X. And the spin-flavor precession occurs between nu E bar and nu X. But of course, when we say that a resonance occurs between two flavors, it's an approximation. There are not actually two approximations here. One approximation is that we assume these two resonances are well separated so that we can treat each one of them as a just two-level quantum mechanical problem, which will not turn out to be true, as I will show at the end of my talk, but for the time being, I'm going to assume it. And the second is that it's also assumed that neutrinos are very close to the flavor, the energy eigenstates are very close to the flavor eigenstates, far from the resonance. So this is also an assumption, which has something to do with the effective mixing angles. And it's actually important for the appearance of the phase effects. So I'm going to spend a few minutes to explain this. So here we see the effective mixing angles, assuming that each resonance occurs between two flavors. So for the MSW resonance, this is the effective mixing angle, which depends only on the density. So density appears in the denominator, which means that at very high density, this angle is very small, in which case the energy eigenstates almost align with flavor eigenstates. By the way, I use this R notation for the energy eigenstate. So R2 means the second energy eigenstate, R3 means the third energy eigenstate. This is not exactly the case in the case of spin flavor precession. Here, the effective mixing angle depends both on the magnetic field in the numerator and the matter density in the denominator. So if near the center, both the matter density and magnetic field are strong, this angle can be small, but it may not be very close to zero. So there's a slight misalignment between energy eigenstates and flavor eigenstates. And this misalignment is actually creates the phase effect. So that will be important. In order to show you how this works, I have to talk a little bit about how the phase effects appear in general. Of course, it's closely connected to the adiabatic evolution and the violation of adiabaticity at the resonance. Adiabatic evolution is something very simple. The evolution is completely determined by the energy eigenstates, by the spectrum. So here I show only two energy eigenstates, and here are my two energy eigenstates. So if the neutrino starts in an energy eigenstate, it stays in the same energy eigenstate as long as the evolution is adiabatic. It picks up a phase, which is a dynamical phase, but this phase is unimportant. That's because what matters is the density operator. And if I write down the density operator, this phase cancels on both sides. And I'm going to write my density operator in the energy eigenbasis, which is what this little e shows here. So this density operator tells me that my neutrino is in the first energy eigenstate with 100% probability. Now, if this neutrino approaches to resonance, now I describe this resonance. We describe this resonance in the Landau-Zener formalism with a matrix like this. Now, P is the Landau-Zener jumping probability. And square root of P is the amplitude for this neutrino to jump into the other energy eigenstate. But this amplitude can be, in general, complex, so there should be a phase here. And that phase is actually called a Stokes phase, denoted by alpha here. So after the resonance, this is what my state will look like. So with some probability, I will be in the first energy eigenstate. With some probability, I will be in the second energy eigenstate. There should be P's here. I'm sorry, I ignored them. But anyway, I just wrote the phases. And there will be a relative phase between these two energy eigenstates plus the Stokes phase. But this relative phase is still not important. Still, I have no phase effects. That's because when I actually write down the density operator, all the phases end up in the off-diagonal terms. And the phases which end up in the off-diagonal terms do not create the phase effect. And the reason is the decoherence. The decoherence, the kinematical decoherence, is the fact that the two energy eigenstates will travel with slightly different speeds. They will have slightly different dispersion relations in matter and in vacuum. And eventually they are going to separate. And if they no longer overlap, they cannot be detected at the same time. So they will lose coherence, basically. So this decoherence occurs at a time scale of 1 million kilometers, roughly. And that I will have an exponential, this exponential term in the off-diagonal terms, e to the minus r divided by r coherence squared. So within the supernova, this decoherence is not important, but it will be important for the neutrinos which arrive at Earth, which is much farther than this distance. So The phases in the off diagonals, because of their season, will not be important. This, however, changes if my neutrino is in a superposition of two eigenstates before the resonance. So here you see before the resonance, my neutrino is in a combination of first energy eigenstate and second energy eigenstates. And as it propagates, a relative phase will be acquired between these two energy eigenstates. Still, no phases in the diagonal term, so these are not important. But if I hit an partial adiabatic resonance, in that case, after the resonance, I'm going to multiply my state with this matrix and do the calculations, whatever. I will end up with a density matrix in this form. And here, now I have phases in the diagonals. And these phases are not going to disappear with decoherence. They will create the phase effect that I want to examine. And the phase which appears here in this exponential terms, e to the minus I5, is a combination of the Stokes phase and the total relative phase that the components acquire from creation up until the resonance point. And this is what creates the phase effect. And it affects actually the detection probabilities at infinite distance at Earth. So in principle, it creates an observable effect, but I say in principle because it's very difficult to actually observe it. And the reason is that this phase depends very, very sensitively on the neutrino energy and also on the external conditions. So it will oscillate very fast. It will be very difficult to experimentally detect it, but still it's important for a number of reasons. Since we cannot calculate it exactly, it's very sensitive. It's actually much better to treat this term as an uncertainty in the survival probabilities after the decoherence. And if we do this, we end up with something like this. At infinite distance, say at Earth, my density matrix would look like this. The off-diagonal terms vanished due to decoherence, and the energy eigenbasis is reduced to the mass eigenbasis, basically, in vacuum. So I'll end up with a density matrix like this. So here, this red part is what I call a classical part, because it looks like a classical addition of probabilities. And the pink part is the uncertainty which comes from the phase effects, basically. So the survival probabilities at Earth would have a classical probability part plus minus phase effect. So graphically, it would look something like this. So here, I'm showing the survival probability of an electron antineutrino at 5-second post-bounce in the model that we used. And here, this red line corresponds to the classical result. And this pink region is the uncertainty region corresponding to the phase effect, the uncertainty. Both come from the analytical calculations, and the black dots come from the numerical simulations. So basically, each black dot is a neutrino arriving at Earth. And each one ends up in the region that I expect them to. What is the catch here? So what we did, for each run, we also slightly varied the external conditions. I mean, if you kept the external conditions constant and just plotted the survival probability versus energy, you would just end up with very fast oscillations here. And this is what is familiar to most people when I say phase effects. But I think it is more realistic to think phase effects as a randomization, because each neutrino will experience slightly different external conditions. They will, travel with different angles and, turbulence, whatever. So it's better to think of it as a randomization, as an uncertainty. So when I say we vary the external conditions a bit, I mean the magnetic field profile, matter profile. We just touched things at a very small scale. And of course, many people actually are familiar with the phase effects. It's not that we found them. And most people actually are just happy with averaging them over and ignoring them, which is appropriate for most purposes. Because, I mean, if you are calculating something like a reaction rate or looking at the detection of neutrinos, you can imagine that you have many neutrinos in each energy beam, and you can just average over this distribution and end up on the classical line. So for most purposes, it is appropriate to ignore the phase effects. As for even in the detection, I mean, if the supernova is nearby, you detect many neutrinos in each energy beam. Their averaged effect would be the same as the classical result. Actually, the only situation that I can think of people could be interested in phase effects is that maybe you want to know what's happening in your simulation exactly. Or maybe you assume that the supernova is far away and you cannot detect many neutrinos in an energy beam. Say you detect only one neutrino in each energy beam. In that case, you can detect one neutrino here, one neutrino here, one neutrino here. So it would look more randomized perhaps. And if there is a really good energy resolution, in principle, you can detect it, but it actually requires a very good energy resolution. However, we got interested in spin flavor precession phase effects because we were actually looking at some other problem. And there was spin flavor precession phase effects in the problem that we were looking at, and we noticed some strange things with it that we didn't expect. Then we looked further into this. So basically, what I'm trying to communicate today is that spin flavor precession phase effects are different from the MSW phase effects that most people are familiar in two aspects. And the first aspect is that spin flavor precession phase effect can appear with only one partial adiabatic resonance, whereas in the case of MSW resonance, you need two partial adiabatic resonances. And the reason is that in the case of MSW resonances, you need two partial adiabatic resonances because neutrinos are already born into energy eigenstates. Because if there are no large magnetic moments, you have the off-diagonal term 0 in your Hamiltonian, and only the diagonal terms, which are matter terms, dominant, which gives you flavor eigenstates as the energy eigenstates. In that case, you need two resonances. The first MSW resonance sends the neutrinos into superposition states, and the second MSW resonance creates the phase. So this is why you need two. And for you to get two MSW resonances, you actually have to wait until late times for this dip in the density profile to be created. So MSW phase effects actually appear later. But spin flavor phase effects appear immediately. That's because if the magnetic moment is large, then in addition to the matter terms in the diagonal, you have magnetic moment terms in the off diagonal. So your neutrinos are not born into energy eigenstates. Because a neutrino born with a definite flavor and definite helicity cannot be an eigenstate of this Hamiltonian. As a result, only one spin flavor precession is enough. So here, for example, we see this. Here I set mixing angle to 0 so that every oscillation, the oscillations here are due to spin flavor precession only. And here you see a spin flavor precession at about 800 kilometers. And the red line is the classically expected average result, and the pink region around it is again the phase effect. And these oscillations are going to die eventually at infinite distance. And you can see at the end, you will end up with a limiting survival probability above the classical line, here below the classical line, here again below the classical line. This is, all three are for the same energy neutrino, but the external conditions are slightly different. So after one resonance, the spin flavor precession phase effects appear. The second and more interesting thing actually appears when the mixing angle is not zero and you have both MSW and spin flavor resonances at the same time. In which case I have two resonances and two jumping probabilities. Here PB is the Landau-Zener jumping probability for spin flavor precession resonance, and PM is for MSW resonance, and for matter B for magnetic field. So if you write down the density operators at infinite distance in the mass basis, you end up with a diagonal, again, matrix, because off diagonals decohere. And I couldn't write down all the terms because they're just too long. So it's the same, but it's the same, the classical plus minus phase effect, classical plus minus phase effect. I just wrote this term as an example. The red line is the classical result, and the first line here is the phase effects due to spin flavor precession, and the second line is the phase effects due to MSW resonance. So they overlap and superimpose on each other. So both are present. So what do they look like? They look like this. Here you see again the analytical results, which is the red line and the uncertainty region around it. And black dots are the numerical results. So the first column is for a magnetic moment, which is of the order of 10 to the minus 16 Bohr magneton. And this is for 5 times 10 to the minus 16 Bohr magneton. And this is for 10 to the minus 15 Bohr magneton. And here we notice the second important difference between the MSW resonance and MSW and spin flavor precession phase. And that difference is the following. So if you look at here, in the first column, all the black dots are in the pink region. So that means my analytical expectations and the numerical results agree. Here, again, the same thing, but at late times, I have some of my black dots going outside the region. And if I increase the magnetic moment a little bit, you see, analytically, I don't expect to have any phase effects because there's no pink region around the classical results. So I don't expect to have any phase effects for large magnetic moments. It's somewhat counterintuitive, but I'll explain in a moment. But you see, numerically, I'll still have phase effects. The reason is the overlap between the two resonances. So what happens is that, so this is the same column, the last column. Oh, sorry. This is the same column. That should be minus 10 to the minus 15, yes. This is the same column. So for large magnetic moments, spin flavor precession resonance becomes adiabatic. So I don't expect to have any phase effects for the electron neutrino survival, electron anti-neutrino survival probability. The MSW phase effects are irrelevant because in normal hierarchy, MSW resonance occurs in neutrino sector. So I don't expect to have any phase effects, but I still have phase effects. And the reason is that for large magnetic moments, at late times, the spin flavor precession resonance starts to broaden and overlap with the MSW resonance. And when this happens, I actually lose all my predictive power from the analytical expectation. I mean, if both resonances seem to be adiabatic, I calculate the adiabaticity parameter, which is large, but it has no meaning because Landau-Zener formalism actually collapses here. And the reason that this happens is because at late times, at late post-bounce times, you see both resonances actually move inward. Both the MSW resonance moves inward. So at for example, 0, it happens here. Okay, let's look at spin flavor precession resonance. At 0, it happens here. But at later times, it happens in the inner regions of the supernova. And when this happens, I get a broader resonance, basically. And this has something to do with the fact that MSW resonance is a universal resonance. But spin flavor precession resonance is not universal. Here, the universal in the sense that everything depends, in the case of MSW resonance, everything depends on the density scale. It doesn't depend on how this density is spread across physical space. That's because if I look at the mixing angle, again, it just depends on the density and nothing else. The width of the density is measured by this parameter. So this is what I'm drawing here. The MSW resonance is this black line, and it doesn't depend on time. But the spin Pehlivan resonance depends on magnetic field as well. So at late times, the spin Pehlivan resonance moves inward, and as it moves inwards, it goes into stronger and stronger magnetic field region. And that makes the resonance wider and wider. And at some point, it starts to overlap with the MSW resonance, which turns the whole problem into a three-level quantum mechanical problem, which I cannot solve at the moment. So this is the second important difference. I mean, the phase effects in the MSW case can appear when you don't expect them to appear. So they are surprise phase effects, if you like. We also looked at the observability of the phase effects. I mean, we didn't have much hope to begin with, but we still looked at them. So this is the Dune event rates for a supernova at 10 kiloparsec away. And the black lines are electron-like events on argon. And these blue lines here are positron-type events, again on argon. So this first, the upper picture is for zero magnetic moment. So you see, if the magnetic moment is zero, I have these phase effects only at late times. And the second picture here, the one in, here, is for 5 times 10 to the minus 16 Bohr magneton. And here I see that the phase effects appear even from the start. So the upper panels assume that the lepton energy can be perfectly reconstructed. So I assume a perfect detector. But the lower ones actually take into account the finite resolution of the detector, and you see all the phase effects are lost in the lower parts. Although I see the effects of the neutrino magnetic moments. For example, the electron-like events are reduced, and electron anti-neutrino type events are increased in the lower picture. And this is for an even larger neutrino magnetic moment, 5 times 10 to the minus 15 Bohr magneton. Here again, the ones at the beginning I see are spin Pehlivan precession phase effects, and the ones that appear at late times are a combination of spin Pehlivan precession and MSW phase effects. So in conclusion, I can say that in general, we expect the spin Pehlivan precession phase effects to appear earlier, even from the start, than the MSW phase effects. And spin Pehlivan precession phase effects may appear even when all resonances are seemingly adiabatic. That's because spin Pehlivan precession resonance is not universal. It becomes broader at later times. And for future work, I think the investigation of this coupling effect between spin Pehlivan precession and MSW precession phase effects, MSW phase effects, can be interesting because, I mean, we just noticed it, but we didn't delve deep into it. So I wonder if even at later times, these coupling effects lead to some observable phase effects. I don't know. I mean, it's something that we should look at. We also kept the electron fraction constants. It will be interesting to look at how things depend on the electron fraction. And also, we didn't take into account collective oscillations. The coupling between collective oscillations, their resonances, and the other resonances would also be interesting. Thank you very much.
Thank you. So time for questions, and I already have one, I think. So I would like to know what is the resolution that you have considered. I mean, one sees that by considering the detector resolution, you get the effects get smeared out, no?
That's that.
What is the energy resolution that you have assumed that smears out all the phase effects?
For the for the Dune detector,
yeah.
It depends on energy. It's an energy-dependent energy resolution. There's a function. I just took the function and folded with it. So from the dual website,
website.
it's not a fixed energy resolution.
Okay.
It's better at low and it's better at high energies and not so good at low energies.
Okay.
That's a
But
fun.
so from the figures, one sees that the phase effects are smeared out, and that was also the case when people study phase effects coming from shock waves. You remember the earlier work of Foglilisi,
I know.
and Mirizzi, and then there were works by Dasgupta and Dige, and the conclusion there was very similar, that the phase effects would be smeared out by the energy resolution. So this is a similar, what you get is along the same lines.
Along the same line, but I'm also optimistic because as these two resonances, if they overlap a little bit more, these three-level effects, maybe they may lead to interesting observation.
I agree that can be a very interesting thing to explore.
It's a possibility.
Yeah, a possibility. Yes. Okay.
But not in this case.
Okay, thank you.
Okay.
Other questions? Yes.
Hello, I have a very nice question that you said that for larger magnetic moment, your resonance is nearly adiabatic, right? So does it mean that your mass or energy eigenstates are nearly your flavor eigenstates, or there is no mixing or the oscillation freezes?
No, there will be mixing. I mean, it's just going to go through the resonance in an adiabatic way. So it will stay in the same energy state, but that energy eigenstate will change flavor content. So there will be flavor evolution, of course, but it will just follow the change of the energy eigenstate. It will not jump from one energy eigenstate to the other. But there will be, of course, there will be.
I was sure. Sergey. Yeah, sure.
No, you're using Landau-Zener. Landau-Zener is derived for linear change of density. And Landau-Zener may work here if the width of the resonance is very narrow, and you can approximate the change of density in this narrow path with a linear function.
Yes.
However, there are better functions that describe non-adiabatic transitions. There is the double exponential, which works very well for supernova neutrinos and so on. So probably we should discuss.
I'm actually aware of it, but we didn't apply it to this one yet. But yes, I mean, one can approximate the change of the density with these functions.
There is a paper of Foley, I think, where they give an analytic description of the change of density. And of course, it's very far from linear.
Okay, thank you.
So thanks for this interesting talk. So I have a quick question. If you go back to those slide 3 or 4, where you have your magnetic field.
That one?
I think it was slide 5 or 4. 5, perhaps.
5.
4.
Oh, okay. Sorry. All right. Yeah.
Or 4, perhaps.
4?
Previous one, yeah.
Okay.
So when we are talking about this magnetic field, this is a huge magnetic field.
Yeah.
So like it's already even below the shock can be 10 to the 13, 10 to the 14 Gauss. So and we know that if the magnetic field is so large, then below the shock it can already lead to the equipartition among different neutrino flavors. But then does it mean that this effect will be totally erased, or
if there's equipartition between neutrino flavors? Yeah, probably it would the way. That's right. I mean, if particularly if there's equipartition between neutrinos and anti-neutrinos too.
Yes,
then yeah, it would. Exactly. But the magnetic field doesn't have to be that large. I mean, because what matters is mu b multiplication. With a smaller magnetic field, the same conclusion could be given for a larger magnetic moment. So if the magnetic moment is 10 to the 13 Gauss, for example, but magnetic moment is larger by 2 orders of magnitude. So this is why I mean, what matters is mu b. So this b is a bit arbitrary. This is not even the full magnetic field. It's only the component of the magnetic field perpendicular. So
Yeah. Sergey.
I have another questions. I mean, I'm not sure that. So you work with Majorana mass eigenstates?
Majorana, yes.
Okay. Then also in one of the cases, you said that the initial state is a linear combination of flavor states.
Yes.
But then it seems to me that in this case, Majorana phases may be important.
Majorana phases.
Yes. But I mean, it's a general, very general statement. I don't know whether in this specific environment that you're considering, this will be the case. But there will be at least one physical Majorana phase with two neutrinos, with two Majorana neutrinos, and this may have some effect. Maybe,
Okay, yeah.
maybe, I don't know.
Yeah, maybe they would at least at a constant. But still, the total phases between. So I'm actually assuming that the total phases between minus pi and plus pi. So, but I mean, well, it's worth looking into. Thank you.
Yes, that's true. Yeah.
You had this formula that was like, it was like a classical part. You had the formula that was like a classical part plus the phase effect.
Yes.
I was wondering if you could go back to that, and I just got lost in what all the symbols meant.
Okay. This one?
Yeah. Yeah. So could you just like explain those diagonal entries, what all the symbols mean there? Alpha, beta,
That
and
one?
P. No, on the slide that you were just at, and
Okay.
at the top. Could you explain where that formula for rho of infinity comes from? What are P,
You mean
alpha, and beta
the
again?
classical part?
The whole thing. What
The
are
whole
what are
thing.
and what are
So-
P, alpha, and beta?
I mean, this formula comes from here. So this is my state from before the resonance, okay? So to get the state after the resonance, I multiply it with this matrix. And then I obtain a state. Then I calculate the density matrix corresponding to that state. And then I let it decohere by killing the off-diagonal terms. And I get this formula in this way, I'm sorry, in this way. And also I assume that this phase is can take any value between minus pi and plus pi. So this is what gives this plus minus sign in front.
What is P again?
P is the Landau-Zener jumping probability. So before the resonance, the probability of being in the first eigenstate is P, and the second alpha square, and the second eigenstate is beta square. So after the resonance with probability 1 minus P, the second eigenstate first jump into the first eigenstate. But with probability P, with 1 minus P, it didn't jump to the second eigenstate, and with probability P, it jumped from the second mass eigenstate to the first. So this is the classical probability.
Is P
part.
not itself related to phi?
What's that?
Is P not related to phi?
Phi. You mean the phase?
Phi, the Stokes phase.
Yeah, they are related. I mean, it's not just, but so what happens is that you can calculate pi, the P, you can calculate P, the jumping probability from Landau-Zener formalism, but it doesn't tell you anything about the phase. Because it actually, Landau-Zener formalism assumes that the jump happens exactly at the resonance point, but it's actually a process. And everything you don't know about the process, you throw into the phase part. So there's a formula to calculate it too, but it's useless to calculate it because it's very sensitive anyway. Okay. But yes, I mean, they are related.
Indeed, a consistent way of calculating the phase effects wouldn't be just solve it numerically
that?
without a consistent way of calculating the phase effects, wouldn't that be just to propagate the states numerically without
Yes.
making any answer from
Exactly.
the hopping probability? I mean, then you retain all the phase information. So I wonder why aren't you doing that?
Yeah, because we don't know external conditions precisely. I mean, I can do this, but do I know the external conditions precisely? It
No,
wouldn't
that's
be.
true, but yeah, I mean, it's another way. I mean, considering it like a statistical effect on the average evolution, is that any better? I mean, wouldn't that be?
Oh, I see. Just I could just have this black dots in my plots and no red line and the pink parts. I still put them to guide the eyes. It's
Yeah.
just that. I mean,
Okay.
but even, for example, when there's
Like-
coupling between the resonances, you can calculate it numerically and see what the phase
can
effect
evaluate
is.
numerical, especially if there is
This
another.
is actually exactly what happened in our previous situation. We got the phase effects and we didn't know where it was coming from because resonances were adiabatic. Then we realized that it is coming because this adiabaticity parameter has no meaning. We have the coupling. This is where we started actually. We worked our way backwards. I'm a bit of a meticulous person, so I want to know everything that is happening inside my computer. That's
Yeah,
why.
as you want to do
Okay.
it, okay. Okay. Other questions or comments? So if not, let us thank Yamach again.
Thank you.